Hello everybody, it is Brianna Burnett again, and today we're talking about Newton's laws of motion. So before we start talking about his laws of motion, let's look specifically at what forces are. So a force is a push or a pull, very, very simple, and they are measured in newtons, which we abbreviate with a capital N. Forces affect speed and velocity, so the more force you apply to something, the faster it's going to go, okay? And if you push something in one direction, it's going to move in that same direction. A balanced force is one that is not moving. So two forces that are perfectly equal create something that is not going to move. An unbalanced force, meaning that one piece of the puzzle has more force than another, means there will be motion. We also have the force of friction, and friction opposes all motion. So it occurs between two objects whose surfaces touch. So like if you rub your hands together, you are creating friction. The rougher the surface, the greater the friction. So for instance, if you are running around, you're in school, you're in a hallway with that real shiny tile floor. If you fall and slide, there's not a whole lot of friction. You'll probably slide for a little bit. You might get a little bit of a scrape, or it might have just hurt from falling, but you won't scratch yourself up very badly. However, if you're running around on concrete and you fall, you're going to scrape your leg to pieces and slow down much faster because the friction is greater on the asphalt road than it was on the waxed shiny tile floor. So let's think about what surfaces make for the greatest friction. What do you think? Some things that might come to mind are sandpaper, asphalt, concrete, carpet has a lot of friction. Anything that slows down motion is going to have a great amount of friction. We also have the force of gravity. So gravity is a force of attraction between objects that is due to their masses. So all matter, we know this, all matter has mass, which means all matter is affected by gravity. Gravitational force increases as mass increases. So as something gets bigger and more massive, it has a greater gravitational force. So if you think about the planets in our solar system, which planet do you think has the greater gravitational force? If you thought Jupiter, you're right, because it is the most massive planet. So gravitational force will decrease as distance increases. So do you think the sun has a greater gravitational pull on Mercury or on Neptune or Pluto? Most likely Mercury, because it is closer to the sun than Neptune and Pluto. So what is the difference between mass and weight? This is a very good video on YouTube by Less Than 5, so let's take a second and watch that.
Our sun is massive. My New Year's resolution is to lose weight. We use these words and phrases practically every day, but what is the difference between mass and weight? The answer is extremely simple, but most people don't actually know what it is. Let's get the scientific physics definitions out of the way first, then we'll discuss what they actually mean in normal people terms. Mass. Mass is a physical body's resistance to acceleration when a net force is applied. Okay, what does that mean in normal people terms? First things first, a physical body is just a fancy name for a collection of matter or stuff. So a physical body could be a planet, a galaxy, a vase, or a puppy, whatever. Next, acceleration is just a fancy way to say how quickly something changes its motion. And last but not least, a net force is just the entire force affecting this collection of matter. So we could rewrite the definition of mass to say how much a collection of stuff can stop itself from changing its motion when something else is trying to move it. That makes more sense, right? So then what is weight? According to physics, weight is the force exerted on a body by gravity. Normal people terms, please. In other words, the Earth is constantly trying to pull everything near it down towards its center. That's how gravity works. And the more mass or stuff something is made of, the more stuff gravity can pull on. Therefore, the stronger the force of gravity gets. So using our two normal people definitions for mass and weight, let's think about an example. Imagine a semi-truck parked in front of your house. Now imagine trying to push that semi-truck down the street. Basically impossible, right? But why? Most people would say it's because the semi is just too heavy, which refers to its weight. But that's not totally true. Actually, the semi simply has too much mass, or is made out of too much stuff. And you pushing on it, aka the force acting on it, is simply not enough to change its motion. So the semi's mass makes it difficult to push down the street. But now imagine if somebody told you to lift the semi-truck off of the street. Also virtually impossible, right? But why? The semi-truck, a recognizable collection of mass, or stuff, is constantly being pulled to the center of the Earth by gravity, which is considered to be its weight. So your attempt to outdo Earth's gravity by lifting the truck away from the Earth is truly an attempt of lifting the semi-truck's weight. Now think about this one for a second. When you visit other planets, you're always made of the same amount of stuff. Your mass never changes, but every planet you visit has different gravity, so your weight changes. You can check what your weight would be on other planets at astronomate.com. So what is the difference between mass and weight? Mass is simply how much stuff or matter something is made out of, and therefore how hard it is to move or change its motion. And weight is how much that collection of mass or stuff is being pulled down by the force of gravity. So now you know the technical difference between mass and weight. And as a result, you are officially smarter than most human beings on planet Earth. Now go forth. Push and lift something made from a lot of stuff resting on a table at a dinner party and officially become the most interesting person in the room. Booyah! We love science. And
All right, so that's just a fun little video that will give you a little bit more information about the difference between mass and weight. So for your notes, if you're a note taker, again, mass is the amount of matter in a given substance, and weight is a measure of how much force, how much gravity is acting on that object, and we measure that in newtons. So I want you to take a second, look at this, and predict. Tell me why you think the crash test dummy keeps moving after the car hits the wall. Why do you think? All right, let's look at why. It's because of Newton's first law of motion. And his first law of motion says an object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line unless acted upon by an unbalanced force. So basically that is saying that an object that is moving in a straight line is going to keep going in a straight line until something stops it or blows it off course, okay? Until something else that has a greater force changes its trajectory. So there's two parts. The first part is objects at rest. Objects at rest aren't moving, obviously. They won't start moving until a push or a pull, a force is exerted on them. They'll stay there forever until a force, whether it's the wind, your hand, an earthquake, something acts upon it. Part 2 is objects in motion. Objects moving with velocity won't stop until something stops them. That could be gravity, that could be friction, that could be the catcher's mitt, that could be a planet if it's sailing through space. It will keep going until something stops them. On Earth, something is always going to stop an object in motion. If nothing else, it will be gravity or friction. However, in space, if gravity isn't acting on an object and that object can just sail and sail and sail and sail, it will keep going until it gets close enough to another celestial body's gravitational field to suck it in, or an asteroid hits it. So let's look at, an example of bumper cars. You've got people driving around all willy-nilly, and as you're moving forward, an unbalanced force from another car acts on your car and changes your motion. So whenever you run into that green car, you're going to hit it and bounce back. The collision changes your car's motion, not your motion. So your body jerks forward while your car goes backwards, okay? But then eventually, the reason you wear that seatbelt is to keep you in line with the car. So as you go forward, that seatbelt's like, no, 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 the car's going backwards. It's going to pull you back with the car. So here's a funny little illustration of Newton's first law of motion. Okay, this is Garfield. And this isn't technically true, but it's still pretty funny. It says, "You're lazy, Garfield." And Garfield says, "I happen to be conducting a scientific experiment, thank you." And John says, "Lazy, lazy." Garfield responds, "I'm testing the first law of physics." John says, "Lazy, lazy, lazy." And Garfield says, "Bodies at rest tend to stay at rest." Now, partially true. Garfield's just trying to get away with being lazy here, but his body isn't going to move until he exerts a force on it or John pushes him off the table, one way or another. So let's do another prediction here. This guy is trying to hit a baseball. He says, "Wow." Let's think about that pitch. What would make him say wow about that pitch? All right, so Newton's second law of motion. The acceleration of an object depends on the mass of the object and the amount of force that is applied. So let's break this law down. Part 1 of Newton's second law says acceleration depends on mass. So if an object has a little bit of mass, you only have to exert a little force to get it moving. But if you want to get it moving very quickly, you've got to exert more force on that object. If you have an object that is very massive, you're going to have to exert a greater force to get it moving. So let's look at the difference between a ping pong ball and a bowling ball. If you are going to move the ping pong ball, you aren't going to have to exert hardly any force whatsoever to make it move a little bit. However, that bowling ball is going to take more muscle, more force to get it to move. The second part says acceleration depends on force. So an object's acceleration increases as the force on the object increases. An object's acceleration decreases as the force on that object decreases. So if you think about, pitchers in baseball or softball, in order to get a quick moving ball, they have to put more force behind that ball to make it go faster. Somebody could just lob a baseball and it'll just kind of float through the air to somebody, or you can pitch it really hard, applying more force to get that ball to go faster and harder. The acceleration of an object is always in the same direction as the force applied. So if I push something this way, the object will go this way. Another part of Newton's second law is the equation force is equal to mass times acceleration, or F is equal to ma. Part of that equation will talk a little bit about gravity and how gravity works. Objects fall to the earth with the same acceleration thanks to gravity, 9.8 meters per second squared. So here's an example that illustrates Newton's second law of motion. You've got a little girl and a little boy on the playground. Little girl says, "Wow, Edison, so close. Your snowball was obviously too massive for the amount of force you put behind it." The snowball never hit her. She goes on to say, applying more force while reducing mass will increase acceleration, thus adding distance. She chucks that snowball at him, hits him square in the face. He says, "From now on, I'm only starting snowball fights with stupid kids." So what he's saying is this girl was very smart and she knew that she had to apply more force to that snowball to get it increase in distance and speed. All right, so here's another prediction I want you to make after looking at these springy gazelles. I think they're gazelles. What do you think is causing them to bounce through the air like that? So Newton's third law of motion explains that, and it says whenever one object exerts a force on a second object, the second exerts an equal and opposite force on the first. So all forces act in pairs. There's always an action force and a reaction force. The forces affect the motion of the object, and they don't act on the same object. So for example, if you look at the space shuttle here, going into space, you'll notice that whenever a rocket launches, they're thrusting out a lot of gas and flames and fuel. As it does that, these gases are pushing down on the Earth. Because there has to be an equal and opposite reaction, the Earth, while we can't physically see it, visibly see it, the Earth is exerting the same amount of force up, which is thereby pushing the rocket into the sky. Same with the rabbit's legs. As the rabbit is pushing on the ground, the Earth is exerting an equal force on the rabbit's legs, causing the rabbit to accelerate upward. So one of the questions might be, why can't I see this happening? You have to remember that in the grand scheme of things on the Earth, we're very, very tiny creatures, and our vision is only so good. So because of the Earth's size compared to us and little rabbits, you can't see the Earth reacting to us, but rest assured it is there. So that wraps up our discussion on Newton's laws of motion. I suggest you go back through and you draw pictures that illustrate each of the laws of motion to you to help you gain a better understanding of that. So the first law of motion says that objects in motion will stay in motion, and objects at rest will stay at rest until something else acts on them. Newton's second law of motion includes the equation force is equal to mass times acceleration, and that equation basically tells us that as you increase the mass of an object, you have to increase the force exerted on it. So the third law of motion says that for every action there is an equal and opposite reaction. And that sums up our lesson for today. I will see you later.